In this first part of section 6.2, we are going to talk about what makes a random variable classify as a binomial random variable. So we're going to look at a few examples here, and we're going to talk about certain conditions or properties that must be met in order to say that your random variable follows a binomial distribution and thus can use the binomial distribution to calculate its probabilities. So the first example that you're given here, we're talking about a situation where your favorite restaurant is giving away a coupon with every purchase of a meal. Notice first you are given a fixed percentage, 20% of the coupons entitle you to a free milkshake. Now we know already percent and probability, those things are equivalent. It's just a matter of how we write that value. So we're being given the probability that we get a coupon with a free milkshake. Now I also want you to notice that there are only two options when you look at your coupons. All right, the two options that you have here, one would be that you get the free milkshake. The other, basically you don't. All right, the other option is that it says better luck next time. When you have situations like this where there are only two possible outcomes for each trial, we call one a success. In this case, the success would be we get the free milkshake. We call the other a failure, right? Which in this case would be you get the coupon that says better luck next time. All right, that is a signal that what you're dealing with may be classified as a binomial random variable, right? Binomial, two possible outcomes. Now, there are a few other things that have to be met and things that we have to check. One looks at the probability that I mentioned just a few minutes ago. All right, it says the probability of success, in our case, a free milkshake, must be the same for every trial. So in our example up here, right, we're told every coupon has a 20% chance, and that's not changing. So in this situation, we do have a fixed probability of success. And when you're dealing with a binomial random variable, that is written or labeled as a value of p. All right, and in this case, it was a 20% chance. All right, the other things that you just want to verify, number 4 says make sure that your trials are independent. That just means what happens on one run of the experiment doesn't affect the other runs of the experiment. And we'll look at a situation where we have to watch out for that in just a minute. Number 1 here says a fixed number of trials are conducted. So that's something else that you want to watch for really carefully when you're verifying whether you have a binomial or not. You have to know how many times the experiment is going to be run, or in this case, how many coupons are you looking at. So notice the next statement here says, suppose that 10 of you order lunch at this restaurant. That's a fixed number of trials. You know right off the bat you're going to look at 10 coupons, and that is your fixed number of trials. And a fixed number of trials, this is another important value for the binomial random variable, n represents the number of trials that are going to be run. All right, the last, notation, if you will, here that we want to watch out for is going to be our random variable, which is our x, right? We talked about x representing numerical outcomes, and we said that typically when we're dealing with a discrete random variable, we're looking to count something. So specifically with the binomial distribution, your random variable will count the number of successes that occur. So in this particular example that we just ran through, the random variable x would count the number of coupons that we get among these 10 trials that say you win a free milkshake, because that is our success in this experiment. All right, now again, once we can determine that a random variable is binomial, then we will be able to use the binomial distribution to find its probabilities and to easily calculate its mean and standard deviation. The key is we're only going to be able to use the binomial distribution if we know that what we have is a binomial random variable. All right, and essentially all we do is check these different conditions. So what I tend to look for first is success and failure, because if you don't have two outcomes, a definite success and failure, then you know right off the bat that what you're dealing with is not binomial, all right? But typically when you're counting something, you do. So like in part A here, let X be the number of times that the coin lands on heads. Okay, the random variable is always counting your success. So right there, I could say that means success for this experiment is heads, and failure, which will be the only other outcome that we're interested in, would be that we don't get heads, right? Or in other words, we get tails. Okay, so we determined, second one here, two possible outcomes. We label one success and the other failure. The next thing that I look for is usually condition 3, making sure the probability of that success, whatever you just said, stays the same for every trial. All right, so if I say that success is getting heads, I could calculate the probability of that success for each time we flip a coin, right? Each time we flip a coin, one outcome is heads. There are two outcomes total, and that is not going to change for any of the trials that I have here. It's not going to change for any of the 10 times that I flip a coin. All right, from there, so I've checked condition 3, probability of success. I can find it and it's not changing. From there, I typically look for my fixed number of trials, make sure I know how many times this experiment is going to be run. And we are going to flip this coin 10 times. All right, so I've got 10 total trials. And then last thing here, just a quick check of 4 and 5. The trials are independent, right? When you flip a coin, your outcome the first time has no effect on what happens the second time. In other words, we could get heads all 10 times, or it could flip back and forth. Heads, tails, heads, tails. It's completely random. So one is not affecting the others, right? These are independent, and we know already the random variable is counting the number of successes. So if I make it through all of those conditions and I don't get hung up anywhere, then I would say yes, this is a binomial random variable. All right, so let's go to part B and let's see if we can do the same thing. All right, I'm going to start with my success and failure. So we have 5 basketball players attempting a free throw, and X is the number of free throws made. Okay, so for a binomial, again, random variable always counts the number of successes. And in this case, we're saying that a success is a free throw that is made. And then I could just flip that around and I could say a failure on the other side here would be a free throw that is missed. Okay, but 2 outcomes, so I'm good on condition 2. All right, next thing I'm going to do is think about the probability of success. Now, in this example, we're not actually given a probability of success. And so what I'm going to do here is just think about whether it would be the same. All right, so if a success is that a person makes a free throw, all right, what we want to think about is, does every person have the same chance of making a free throw? All right, and the answer there is no, because these players have different strength levels. They have different success rates when it comes to how many free throws they make versus how many free throws they miss. And so what's important here is that the probability of success is not the same for each player, in this case for each trial. Okay, because that probability of success is different for each player, I don't need to go any further. I'm going to stop right there and I'm going to say this is not binomial. And my reason is what I just said. The probability of success is not the same for every player. All right, one more here. 10 cards are in a box, got red and green. 3 will be drawn, and X, random variable, represents the number of red cards drawn. Okay, so again, I'm going to start and make sure that I have a definite success and failure. And like I said, usually when you're counting something, you do. Like let's say, for example, you were going to count the number of times you rolled a 2 on a 6-sided die. You could say, well, your success is that you get a 2, and your failure is just that you don't get a 2. Okay, so you can pretty much always do that. In this case, it's very obvious because we only have 2 possible colors. So we would say our success is that we get a red card. Our failure, generally speaking, would just be that we don't get a red card. But in this case, since we only have one other option, our failure would be that we get a green. All right, so come back up here. I checked property 2, right? 2 possible outcomes. Now I'm going to look for the probability of success. And you have to remember, when you think about the probability of success, you have to think about what happens each time the experiment is run. All right, so like in this case, what I'm going to do is think about the first card that is drawn. All right, the first time that I draw a card, all right, and I go to this box of 10 cards. If I want a red one, my probability would be 5 red out of 10 total. All right, this would be my probability for the first card that I select. All right, but the key thing about binomial is you have to make sure that probability does not change. So now what I'm going to do is I'm going to think about the next trial. All right, the second selection. In that case, if I want a red card, I have to remember that I've already chosen one. Okay, and that card is not in the box anymore. So in this case, for my second selection, I'm only looking at 4 red cards, and I only have 9 total to choose from. Okay, right here, notice the probability of success is not staying the same for every trial. And again, as soon as you hit something that is not satisfied, you don't need to go any further. You would just stop right there and you would say, this is not a binomial random variable. All right, this is what I want you to practice with a little bit before we go through the remainder of this section. Because again, everything else that we talk about in this section, finding probabilities, finding mean and standard deviation, it will only apply to a situation like A, where what we have is binomial. All right, situations like B and C, where the conditions are not met, these methods would not be appropriate to use in those situations. So take some time, go into your homework, look specifically at the problems like this that say decide if you have a binomial random variable, and then we'll address any questions that you have about that, and we will pick up from there, determining probabilities for binomial as well as mean and standard deviation.